Alright, this is another lecture involving salts, but this time what we're going to do is we're going to look at p orbitals. And actually what will happen also is that we'll find a degenerate representation that'll show up, and you'll see how to generate a salc for that representation. So the molecule we'll use for this actually will be square cyclobutadiene. I say square because it'll make a difference as to what point group this ends up being. There's considerable debate whether or not this is actually a square molecule or a rectangular one. And obviously the structure of it has not been determined to nail it down specifically, but for our purposes we're going to assume that this is a square, and then that will put that molecule into the D4H point group. And so, again, it's planar, it's square, it's in D4H, so this is a point group we're familiar with. Let's then look at what would happen if we were to try to generate salcs for this using the projection operator method. So, first of all, let's have a look at the molecule a bit on an edge, like this. And make that bigger. Okay. And what we're going to do is we're going to use the p orbitals that are perpendicular to the plane of the molecule as a basis set. And so, 1, 2, 3, 4 of those. Okay, now as you know with p orbitals, they do have a change in the wave function. They have one angular node, and so we'll have the labels, the lobes that are on the top be positive amplitude, and the ones on the bottom be negative amplitude. Okay, so then the next step is to generate a gamma reducible with all the symmetry elements of the group. And so let's put down the symmetry elements. Now we have to define where the perpendicular axes and everything are going to be. So as we did in class last week or the week before, these are the C2 primes, double primes rather. They don't contain any atoms. These are the C2 primes that do. Those also then will be the locations of the sigma V's, which contain the C2 primes, and the sigma D's, which contain the C2 double primes, consistent with the way that we've been doing it. Let's then generate our reducible representation as follows. Okay. We do nothing to the molecule, all 4 p orbitals remain in place. If we rotate about C4, which is right there, so that is the 2 C4s, collinear C2, and the 2 S4s. If we rotate about that axis, all p orbitals move. Obviously the collinear C2, all p orbitals move. The C2 prime that contains 2 of the atoms, what's going to happen is 2 of the atoms remain fixed. That means 2 of the p orbitals remain fixed, but there's something that's going to happen here that doesn't happen when you're dealing with spherically symmetrical, meaning S-type orbitals. When you have a P-type orbital, what will happen is when we flip this molecule over, the orbital will stay in the same place, but now the negative lobe will be on the top and the positive lobe will be on the bottom. The same will happen over here, and likewise with the other two along the other C2. So the number of unmoved orbitals is 2, but because they flip over, exchanging the positive lobe for the negative one, that is a -2 there. Okay? Then beyond that, the C2 primes that bisect the angles leave nothing where it was. Inversion center, obviously nothing. The S4s, nothing. The sigma V's leave 2p orbitals fixed where they are. But in this case, because the vertical mirror planes are containing these orbitals, they don't reflect one lobe to the other. The lobes remain the same too. And so this is a +2. Because the vertical mirror plane contains those orbitals, it leaves that as a +2. I left the symmetry element out here, so let's get that in there first. All right, the dihedral planes through here move all of orbitals. And now the horizontal mirror plane, which I left out, which has now been put in there, if you reflect about that, you flip this positive lobe but that negative lobe, likewise here, here, and here. So 4 orbitals remain in place, but they turn upside down, and therefore you have a -4 there. So now, if you reduce this, what you'll find is, and this is the way we did in class and we've done in previous virtual lectures here, what we get out is e.g. A2U and B2U. So you can do that exercise yourself to find where these, or how these come out of that. Notice one thing here that we don't see, that we did see when we used s orbitals in ring cells. There is no completely symmetric representation. There's no A1G there, no AG there. P orbitals can never be completely symmetric because they have a node there and they change magnitude design. So once we've reduced that, then we can do the projection operator method. So put that over there to keep track of it. Now remember, for this, you're going to have to define where all of your orbitals are and were. So let's, again, to make this a little bit easier to see, look at the molecule top down. Okay? And the p orbital here, I'm going to call 1, this is 2, this is 3, and that's 4. So we're going to use a p orbital now as the basis set for the projection operator method. And if we go back to our axes and whatnot that we had, that's what we have. Okay, so you have to specify which symmetry elements are which ones in here. And again, when you do that, just stay consistent and you will still have the correct answer come out. So, again, the B4H point group. Now for this, remember you have to actually specify which axis is which. Right, so now we have to break all the classes down into their individual elements. So it involves writing out all 16 parts of this. Right? And so because of that, we've got to label our C2 axes as well. So I'm going to call this one up here C2 number 1. And this one is C2 number 2. We'll also have sigma V number 2 and sigma V number 1 up there. Likewise for this, we'll call this C2 double prime number 1, that one C2 prime, C2 double prime number 2, and the corresponding sigma D. So as we break this all out then, we're going to run out of room. So I'm going to continue this down here. One thing that may have not been pointed out in this point group before is the two S4s. One of them is an S4 in the clockwise fashion, and one is in the counterclockwise fashion, so the other one is S34. So after all that, that's what we get. Now we see how our basis orbital transforms under the operations of the group. So let's pick p orbital number 1. I'll just call that pi 1 instead of sigma 1. And let's see how that transforms as we do the operations to it. If I do nothing to it, it stays where it is, and it's pi 1. If I C4, then it becomes pi 2. A clockwise C4 motion will bring this corner to there, this p orbital to there, and that's why that happens. If we go the other way, counterclockwise, it is pi 4. If we C2 it, we're doing the C4, the clockwise one, twice, 1, 2, it's pi 3, right? C2 double prime 1 is this one. I flip this molecule over. This p orbital stays where it was, except it is flipped over, and therefore it is negative pi 1. The other one, the other C2, will exchange 1 and 3 and flip it over, and therefore it is negative pi 3. The other ones, the C2 double primes, the first one, which we label here, makes that negative pi 4, and the other negative pi 2. So you should see how that goes, right? If I flip over this way along C2 double prime 1, 1 and 4 exchange places, and it's flipped over. If I do it the other way, 1 and 2 is switch places, and that's flipped over. The inversion center takes 1 to 3, but because it's an inversion center, you're actually going through the center of the molecule and down, therefore that is a negative. And the thing about this is, if you did something where you assume that that was a positive sign there, you would not be able to reduce or combine your representations properly. You'd run into an error that wouldn't make any sense, and then you would know that there was something wrong. The S4 will take that to negative pi 2, and the S34 to negative pi 4. And so you should see how that is as well, right? We rotate 90 degrees and reflect. We're up at position 2 and upside down, negative pi 2. We go this way, we exchange 1 and 4 and reflect, so it's negative pi 4. The horizontal mirror plane will just flip the orbital over in place, so that gives you negative pi 1. The vertical mirror plane here doesn't do anything to it either. It leaves that as pi 1. The other mirror plane that we have, this one, exchanges 1 and 3, but doesn't flip the orbital over. So it's written as pi 3. This dihedral plane will exchange 1 and 4. And the other one exchanges 1 and 2. Okay, so now we have all of our transformations in place. We then use the symmetry elements as we did before to transpose the symmetry onto this. And so, if we do that, let's do the A2U first. All you do is you take out your character table and you multiply these by the appropriate values of 1 or negative 1 in order to see what the symmetries are. Okay, so in A2U, for the identity, we have 1. Is this showing up? Yes, it is. And so we have pi 1 plus pi 2, because the character for this operation is 1, plus pi 4, plus pi 3. Because the character under C2 is also a positive 1. Now, we have a negative 1 under C2 prime there. And so we're going to have negative pi 1, negative pi 1 times negative 1, that's plus pi 1. The same thing goes for the other C2 prime, plus pi 3, plus pi 4 from this, plus pi 2, plus pi 3 here, plus pi 2, plus pi 4, plus pi 1, plus pi 1, plus pi 3, plus pi 4, plus pi 2. So you can see all that. And so again, for this, all you do is you take these individual ones, you transpose underneath the characters from A to U, and you put them all together. And so what will happen then is for this representation, A to U is equal to 4 pi 1 plus 4 pi 2 plus 4 pi 3 plus 4 pi 4. So everything's positive. These things that were negative, because the character for both of the C2 primes, the C2 double primes, the inversion center, both of the S in proper axis of rotation, and the horizontal mirror plane were negative 1 in that irreducible representation, those all become positive. And so this is the reduction that you get for that representation. If you do the exact same exercise for B to U, what you find is you get 4 pi 1 minus 4 pi 2 plus 4 pi 3 minus 4 pi 4. So very much like the first one, except we have negative signs. Now the part that we haven't seen before per se, but we will right now, is that we're going to use a degenerate representation, right? Because this one here is degenerate. And so the characters and things like that are 2s and 0s, not all 1s, etc. So I'll write the individual characters on here from EG, and then you can see what they are in the character table. Oh. Okay, so the identity is a 2 because it's doubly degenerate. The next 2 are 0 because the character for the class C4 is 0. For the other C2, it's negative 2. The next 4, both C2 prime and C2 double primes, are 0s. The inversion center is a 2. Both S4s have a character of 0. The horizontal mirror plane is a negative 2, and all the remaining vertical and dihedral mirror planes are 0. Okay. So this is just off of the character table for the irreducible representation EG. If you go through and multiply, obviously some of these are going to not appear at all. And so we just multiply through, and we would find that EG is 4 pi 1 minus 4 pi 3. Okay, so we have a problem now, because what does that actually represent? That's only one orbital. Okay, now if we add 4 atomic orbitals in, we've got to get 4 Selks out. The same rule applies to molecular orbitals as it does basically making a molecular orbital out of this. So we have one component of the degenerate set of Selks with symmetry EG. How do we get the other? I'm going to erase this because we're going to have to do something else. And that something else is you pick any one of the other 3 p orbitals that you didn't use before in order to get this to work. So why don't we, instead of pi 1, pick the p orbital on atom number 2, pi 2. So this goes through the exact same exercise again. The only difference is you just have to consider this irreducible representation. So when we're finished, we're going to multiply by the characters for that again, and that will be all you need to do. So here's how these translate. If we do nothing to the molecule, we get pi 2 back. If we do the clockwise C4, it's pi 3, the counterclockwise, clockwise, counterclockwise, pi 1. C2, that's taking the C4 twice, translates us to pi 4. Here we have negative pi 4 and negative pi 2 for the axes of rotation. As you see, this axis that we've labeled C2 prime number 2 contains atom number 2, it just flips it over. The other one exchanges 2 and 4 and flips that over again. So that's where the signage comes in. we get negative pi 3, negative pi 1, negative pi 4 for the inversion center. For the S4, negative pi 3. For the S34, negative pi 1. And then finally, the horizontal flips the orbital over, negative pi 2. Pi 4 and pi 2, pi 3, pi 4 for the other reflections. And so again, that's all there is to that. This will give you the other part of the degenerate set. And so if we multiply again by the characters for this, a lot of these things are going to drop out from this. And what we get then for the other EG is 4 pi 2 minus 4 pi 4. And so the other part of the set is that. And so what happens is we're going to have two SALCs that transform and act as one degenerate pair in this. And so we're done now looking at how the protection operator method pushes these things around to give us the SALCs. The last step is as before, and that's normalization. So we get rid of all this here. And might as well get rid of that too. Let's just keep track of which one's which here. Because there's going to be pictures associated with this one that I'll draw that you can see what the magnitude of the coefficients actually means. Right. So, normalize. Let's normalize A2U. We're going to multiply by L over H. L is the dimension of the representation. It's a one-dimensional representation. So we have a 1, the order of the group. L over H, the order of the group is 16. And we're going to multiply that by our expression here, 4 pi 1 plus 4 pi 2 plus 4 pi 3 plus 4 pi 4. That gives us 1/4 pi 1 plus pi 2 pi 3 plus pi 4. Right, because I get 4 over 16th for each one of these coefficients, that reduces to 1/4. Then I can factor out to 1/4 like that. Then we sum the squares of those and take the square roots. And so we're going to take the square root of 1/4 squared plus 1/4 squared plus 1/4 squared plus 1/4 squared, which is the square root of 4/16, which is the square root of 1/4, which is 1/2. And then we're going to divide this by 1/2. So what do you get? And that is 1/2. So our first normalized self of A2U symmetry is this. Okay. So we can take that away. And we can do now the B2U. L over H, L is the dimension of the representation, which is 1. It's not degenerate, or the group is 16. And so we're going to multiply that times 4 pi 1 minus 4 pi 2 plus 4 pi 3 minus 4 pi 4. All right. So then we're going to go through almost the exact same thing we did last time. This becomes 1/4. Pi 1 minus pi 2 plus pi 3 minus pi 4. We take the sum of the squares of the coefficients. Notice this one is -1/4, but you're going to square it anyway, so it sort of factored itself out of there. When you do that, it's 1/2. If I divide all of this by 1/2, I get 2 over 4, which is 1 over 2. And there you go. Same procedure for both parts of the degenerate set of EG. Note the following thing. All right, if I normalize the coefficients for this one, the normalized coefficient that you have factored out is going to be the same. And so for EG, we're going to have L over H, which is 1 over 16. No, it isn't. This representation is doubly degenerate. So L is 2, and H is still 16. So we're working with 1/8, not 1/16. And so with that, then, let's do the first one. 4 pi 1 minus 4 pi 3 is what we have. This becomes 4 over 8, or 1 over 2, pi 1 minus pi 3. We're then going to take the square root of the sums of the squares of coefficients, 1/2 squared plus -1/2 squared square root of quantity. Negative sign here, negative sign here. What do we get? We get the square root of 2/4, which is the square root of 1/2. And that is 1 over the square root of 2, or the square root of 2 over 2 if you aren't comfortable leaving it that way because your teacher in grade school made you do it. But it turns out we don't need to do anything with that right now. And so we're going to divide this whole thing by 1 over the square root of 2. And when you're done, what you get is the square root of 2 over 2 pi 1 minus pi 3. The other degenerate will go exactly the same way, except that the components are pi 2 minus pi 4. So the normalization is the same. So there we go, 4 selks out of 4 p orbitals. What do these look like? Well, let's draw the molecule. Again, on sort of an edge-on sort of way. What does A2U look like? All of these have positive magnitude. And so A2U is the one where all of the positive lobes will point up and all the negative lobes will point down. And so this is the type of orbital, for example, that could act or interact with a metal s orbital or a pz orbital or something like that if you coordinated this to a transition metal. What does B2U look like? Well, if in position 1 we have a positive magnitude, in position 2, which is the corner in the back there, it's the reverse. Since 3 is positive and 4 is negative, this lobe and that lobe, the top lobes, the upper lobes on atoms 2 and 4 are flipped upside down. Okay? And finally, this set transforms as a pair. So, we have a set of 2 orbitals now. Where we've got amplitude on carbons 1 and 3, that's this one. Or we have amplitude on carbons 2 and 4. That's this one. So this is the EG set. Since this one is positive, if this one is negative, it's upside down. Pi 2 is positive. This one. It's like that. Now it turns out, if you look at this, the square root of 2 over 2, if you do the calculation on the calculator, if I can find it on the calculator. There we go. Right, the square root of 2 over 2 is 0.707. This is obviously 0.5. So, another thing to note in these that you'll see if somebody draws these out for you, right, because the coefficients in front of all of these are the same, 1/2, 1/2, 1/2, and 1/2, the sizes, the relative sizes of those orbitals are the same. These would be larger lobes than those, because that's somewhat bigger. But the size of this lobe and the size of that lobe, as well as this one and that one, are the same. And so that's how one generates a pi-type selk set. Another thing to note, if you care to, is the inversion center is still right in the center of the molecule. This flips upside down, but you have positive amplitude here and positive amplitude there. Therefore, that is Gerada with respect to the inversion center. These are both ungerada. If you go through the inversion center, you change positive to negative. And so that also holds for these. And so that is the second lecture on the construction of cells.